the last speaker of this session, Kevin Mato. Kevin is a master student at the Department of Electronics, Information and Bioengineering of Polytechnic of Milan, and is going to talk about quantum annealing approach to the molecular unfolding problem. Please, Kevin, go ahead.
I will share my screen.
Yes.
Hello, everyone. I'm Kevin Mato from the Polytechnic of Milan, and today we'll talk about molecular unfolding with quantum annealing. So the project is with drug discovery, in particular in silico drug discovery, which aims at screening virtual libraries of the order of billions of compounds for the most suitable molecules to forward to the later experimental phases. A computational technique used for this reason is molecular docking, which is the method to calculate the preferred position and the shape of one molecule to a second one when bound to each other by means of rototranslations. The evaluation of each molecule based on pharmacophoric features is very computationally challenging, so a geometric approach becomes a more viable method for sampling the solution space. Problems arise because the initial shape of the substance is chosen from a tool a priori. It's reproducible but disconnected from any criteria. So this can be defined as a type of shape bias which must be removed in order to perform the molecular docking and have nice results in terms of quality. So with our work, we focused on just studying and improving the compound shape and actually not on the spatial position inside the protein pocket. So let's go with the problem definition. We can think of the ligand as a flexible set of atoms with the chemical bonds or edges fixed at a certain length, and where consecutive bonds are have a predetermined angle. A subset of these edges will be defined as rotable. The rotable bond or torsional are bonds that split the molecule into two non-empty disjointed fragments when virtually removed from the molecule. And these two portions of the compound, when they are detected, can rotate independently from each other around the axis of the rotable bond. The relative position of one fragment with respect to the other is what determines the so-called conformation of the molecule. We can assign to each fragment we can assign to each fragment a certain angle, and each of these angles will be our variables in the model of the molecule. We use the term conformation as synonymous for this set of assignments, and the final objective is to find the unfolded configuration that maximizes the molecular volume, or equivalently, that maximizes the distance between fragments. So each torsional is associated with a rotation matrix, and in the case two atoms will be connected from a path that will contain more rotable bonds, the rotation matrix will be just a multiplication of the single rotational matrices. So we proceed by virtually dividing our molecule into fragments. The first starting point is to select all the possible dimensions of the solution space by iteratively picking out the rotable bonds. And afterwards, we calculate the betweenness centrality of each atom. This attribute allows us to define an ordering of the atoms inside the molecule. And this attribute defines the degree of centrality of the atom inside the graph of the chemical substance. Each fragment is then defined as a set of atoms influenced by the same set of rotable bonds, which we call a rotables influence set. We calculate the influence set as the intersection of the rotable bonds and the edges of the shortest path from a generic atom to the central atom. All the atoms in a fragment are then mapped to a virtual path composed of the edges in the influence set, and then the relative composite rotational matrix is created. So let's talk about the combinatorial optimization problem. Mathematically, finding the unfolded configuration means maximizing the internal distances in function of the theta angles of the rotatable bonds. Here, dA theta denotes the distance between fragment A and fragment B, while the big theta is the sum, capital theta is the sum of the fragments distances squared. The theta will depend on the set of torsions assigned to the shortest path between two fragments. So we want now to transform our problem in a binary optimization problem. The problem is inherently high order, so we will get a HUBO or a high order unconstrained binary optimization problem. Let's consider discretization of the angle theta I associated to a torsional theta I into d values. This induces a discretization on the sines and cosines for each torsional ti, again into d values. We defined a binary variable xik with k between 1 and d, such that the binary variable is 1 if our torsional angle assumes value theta k, otherwise 0. And on the right, we can see the constraint that explains that in our problem, a torsional can assume only one value at a time between these discrete values. In the end, our rotational matrices will be a function of our binary variables. So this is the general form of the HUBO optimization function, where the first term is associated to the hard constraint explained before, multiplied by constant A, and the second term is the term associated to the optimization of our problem. In general, we have to pay attention that dA theta could depend on m torsionals at the same time. So the terms could go to up to the mth order inside the second term, and in general, the HUBO could have terms of the order of 2m. Now, let's talk about the problem structure. In order to obtain a precision delta theta I, we have to define the number of variables needed to achieve this precision. And the number of variables will be d. And given a molecule with m rotables, the total number of binary variables will be d times m. The example of molecule that we used is the one on the right side, with 82 atoms, 40 fragments, and 20 rotable bonds. It's a quite difficult molecule. Here, we're talking about the choice of the precision. Here we have on the left a plot with 118 compounds ordered by increasing volume, and it explains the degradation effect on the final expanded volume when we increase the precision of rotation from 1 degree up to 45. We chose for our experiments a precision of pi/4 as the maximum degradation for this rotation step is just 4%. On the right, you can see that these positive results aren't due to the initial shape of the compounds, since our procedure got an average 70% of volume gain. So the HUBO, when the precision chosen is pi/4, has a number of linear terms increasing linearly. We go from 16 for 2 rotables up to 80 for 10. And the number of high order terms, included the quadratic ones, are going up to 12 millions in the case of 10 rotables. Okay, we had to face a lot of problems to achieve actually the implementation on real quantum annealers. But a way to overcome this problem is to apply some approximation on the HUBO. We deleted the terms under terms that had the coefficient under a certain threshold, and this allowed to speed up the construction of the HUBOs, to transform the HUBOs into QUBOs, and this was done thanks to the function make quadratic from the D-wave libraries. And this made the problem solvable on D waves 2000Q and advantage. On the color aqua column is there is the full HUBO, and while we increase the threshold from 100 to 1500, we can see a decrease in the number of terms in the HUBO. Pay attention that when the threshold is too high, we are invalidating the HUBO. After deriving the HUBOs for the different thresholds, we see another development in the number of terms, both linear and quadratic. This is very interesting, and this is related to the embeddings on D waves 2000Q and advantage. Now we can see that the physical implementation of the HUBOs deeply vary depending on the topology on which we perform the embedding. The Pegasus topology of advantage gives the opportunity of solving the problem for 10 rotable bonds with a number of physical variables slightly comparable with the 5 and 8 rotables solution on the Chimera topology of the 2000Q. This makes a difference between solving a simple molecule or a complex one. We can expect better solutions in terms of quality with advantage, since the average maximal chain embedded can be less than half in advantage compared to 2000Q. Okay, here we have some results. We have on the left the comparison on terms of quality between advantage 2000Q and some classical methods. In this case, the classical methods are just some naive enumerative inspection of the solution space, and with a mix also in some cases when it was to compute computationally challenging with some greedy variance of the enumerative solution. So we can see that advantage, as we expected, is better in terms of quality or volume with respect to the wave 2000Q. And on the right, we can see how the solution scale. Obviously, the classical solution had the worst scaling, but it's surprising because, as we could expect, the quantum annealers have better scaling, but 2000Q had a slightly better scaling than advantage. The conclusions. We tackled the problem of molecular unfolding, and we created new HUBO and HUBO formulations that could be solved on real D-wave quantum annealers. We have observed that by increasing the terms cutoff threshold, as the problem size becomes bigger, it becomes possible to embed formulations that couldn't be otherwise. Embedding our problem on advantage compared to the D-wave 2000Q cost 52% less in terms of physical qubits, and with chains 49.7% shorter. The volumes obtained with advantage are better than those of 2000Q by 6.82%, and the scaling on average of 2000Q is 36.02%. That's it. Thanks.
Thank you, Kevin, for the nice presentation. I think I have a very quick question. If you go back to the slide where you present the number of HUBO variables.
Here or here?
Or maybe of HUBO variables. Yeah, maybe here. Okay, I see that on the left part for 6 there is a decrease in the number of variables. Do you think this is in general true, or depends on the particular molecule?
I think this is an effect related to the molecule. In fact, the problem is slightly changing just by adding always one rotable. The problem is completely different every time we add a new rotable. And by going from 5 to 6, we can see some elimination of between terms due to the presence of the terms related to the last rotable. In fact, you can see that this situation is also reflecting in the scaling and the volume achieved by the classical solution.
Okay. Thank you very much for your presentation. This was the last presentation of this session. I think we have something like a 10-minute break. After that, we can continue with the second afternoon session. And yes, that's it. See you in 10 minutes.